So, what we are going to do for now is we're going to start to play the campaign, and I'm going to explain you a little bit about digital logic and assembler. Congratulations, you've been abducted. We're testing you. The rules are simple. Build a functioning computer, or you will be eaten. Good luck. So here we go. A signal flows from the input to the output. In the upper left corner, under input, there's a green icon. Click on it to turn the input component on and off. Here we go. We are very impressed with how well you completed this last test. Instructions: click any of the gray buttons in the last row. Oh, okay, see, we've decided you're probably not a plan. See, in this level, the challenge is to figure out how an AND component works. Be sure to figure it out before you complete this level, or you will get stuck next level. So here we are. This is an AND gate. This is a logical component, and this is basically a truth table. And an AND gate, we can test it like this. You see? And an AND gate, I don't know if maybe you can guess it. It is always true. The only case where it is not true is the case in which both, like it is not AND, right? And AND would be both are true, both inputs are true. Correct, you've unlocked the NAND gate. With this component you can build everything else in your computer. Yes, the NAND gate. This is okay, interesting fact is this is a transistor. This is basically a transistor. We have an input and an output, and every time you put a current on one of its legs, it would lock down, right? It is a little bit like a little switch. I actually have transistors here, I could show you. One second. Transistor assortments. These things right here. These are transistors. And yeah. It has an in and out. And basically a switch component. Which one was this? This is, of course, it's not possible to identify it. Oh, of course, the name is number. Please, I was just in the wrong field. So, this game is the link piece between it's the it is like the baseline is electronics, right? And once you build complex electronic structures, this game teaches you a lot about how, if you want to, right? This game teaches you a lot about how you use logic, you use so-called digital logic to describe complex circuits, and as we're going to see most components, now that we have unlocked the NAND gate, it is time for us to build our circuit. That level describes the circuit, and this level will build the circuit that matches the table. Alright, the NOT gate. Okay, let's build a NOT gate. See, as we are going to see in these first few levels, the NAND gate, the basic transistor, is basically the key component that makes up all the other components. Okay, this is a NOT, right? Now we, by the way, look, now we unlock the NOT gate component. It's amazing. I highly recommend you play this game, and I highly recommend you to play the game probably even before you watch my videos, or maybe while watching my videos, at least. I don't know. I feel like you should try and solve the levels before you watch my instructions. No. Not good. Make an AND gate into a NAND gate. As I said, look, now we have these three gates: the AND gate, the NOR gate, and the OR gate. And these, which are these three components, by the way, and this is what I love about this game so much. These components are actually the way they look, right? This is actually the same way they would look in a schematic for actual electronic logic. And if you have some basic electronic knowledge, this game is going to teach you, or is going to enable you to basically build a functional computer. And yeah, it's an amazing playstyle, in my opinion. Anyway, I was going to talk about the NAND gate and how transistors make up basically all of digital logic. Now, next thing we have is the AND gate. Right now, the elephant is dominating all the other test subjects from us. Adjusting for brain size, you are also doing well. Create the circuit that matches the table. Double click the component and move it together with the connected wires. Okay, look. Now we have an AND gate, right? And an AND gate is basically, since we know that an AND gate produces an output that is the opposite of this output, right? We would use an AND gate just to negate, because we remember that using an AND gate like this creates a NOT gate. And this is going to solve the level. So here's the next thing, the NOR gate. Most creatures on Earth are aggressive and cannot focus. To succeed, you must learn to think logically and not destroying things. Double click on a component to move it together with the connected wires. See, first of all, what we see is that we in this case have an output that looks a lot like the NAND gate, but it's basically inverted. So if we negate the inputs, I'm not sure if there's a solution. Do we have to negate it? No, I think we have to negate it. Do we though? Yes, we do have to. So this should solve the level. So this negates the input, the first input, this negates the second input. And the moment we feed it into the NAND gate, we basically have negated input, which would create a NAND gate that would give us false, true, true, true. And if we negate the output of this NAND gate, maybe you can imagine this, we would create exactly what we needed. True, false, false, false. Onwards. The next component. should be happy to participate in our various tests. Get a chance to communicate with very advanced people from the galactic civilization. Create the circuit that matches the table. Create the circuit that matches the table. Yeah, okay. This is an OR gate. And an OR gate is basically always true. When one of the inputs or more are true. And since we just created the NOR gate, which is the negated OR gate, if that makes sense, we have an easy time just creating this circuit. And since I just explained the NOR gate, which is, as I said, basically the NAND gate with negated inputs, we have this one, which is one step simpler. Here we go, always on. Create a circuit that is always on. This level is, yeah. This level unlocks your first manual page. This one is important. Make sure you understand it. Look, this table basically tells you what I just explained to you. The truth table of the 4 fundamental gates are symmetrical. You can convert them by inverting the input, vertical arrows, or inverting the output, horizontal arrows, as indicated by the graphic below. You can get from any basic gate or any other. At most, you have to not both inputs and outputs. You can go between OR, NOR by inverting the outputs. The same goes and NAND. In fact, NOR means not OR, NAND means not AND. I hope this makes sense. I feel like, I don't know, I feel like I've just explained this. Notice the component shape of OR, NOR are identical except for the little dot at the tip, which means not AND. Getting inputs, no. Look, wait a second. I'm gonna show you the thing. Hopefully this is not working. Great. This website is called Geeks for Geeks. I'm gonna add this to my bookmarks toolbar again. This website is called Geeks for Geeks. Wait a second. And it shows you the basics of digital logic. Digital logic gates are the fundamental building blocks in digital electronics, used to perform logical operations based on the inputs provided to it, and gives a logical output that can either high 1 or low 0. The operations of logic is based on Boolean algebra or mathematics. Well, you see, we have the AND gate, and you can see the truth table, right? Speed the graphics. See? This is an OR gate. If you look at the game, right? If you look at the game, this is the OR gates. The NAND gates. And the NOR gates. And maybe as you can see, go further in which is this dot means negation, right? And this shape is an OR, this shape is an AND, and these are, as you can see, oh, there's the NOT gate as well. NOR gates, NAND gates, XOR gate. We're gonna meet this, encounter this gate as well. XOR gates. Yes. Or XOR gate is basically, it's an exclusive order. We're gonna encounter all of these gates. NAND. You can see the, I guess you can see the, see what this is about. You can see that the game basically allows you to as you know, these tests culminate in building a functional computer. Species that are capable of finishing are considered sentient by law. This is the main reason we don't need you afterwards. I'll put on the second tick only. Second tick only. Oh, alright. Because this is structured in clocks. Second tick only. That's interesting. Okay. In this case we would use an AND gate. This is the easiest variant. You see, this is structured in ticks, and when we're talking about computers, computers live by clock speeds and ticks. Maybe you know this from gaming as well. And it steps. Like, you can imagine this like electric pulses that go one step, one by one. In this step we get no signals on our inputs. In this step we get one input. On this step we get another one. On this step, and these are just, I don't know, happens, I don't know if you know this, but in general, computers run by clock speed, right? And these clock speeds describe basically how many of these pulses we can send through the system per second. I guess this is what hertz is, if I remember this correctly. It's been a while. Is it the door gate? Let's go. Last level, you built a circuit that was green when that gave us a true when we were at the second tick. This level built a circuit that is green when we are at the second or third tick. This is also known as a XOR gate. This level is difficult, so don't be discouraged if you don't get the answer right away. You can connect one output to more than one gate. These two are false, this one is. Alright, this is a XOR gate, which is an exclusive OR. And how exactly do we do this? I'm not sure. I'm not quite sure right now. So this is NAND. I mean, we could go and of course we could go and A and not B, not A and B. And this would solve it. And then we use an OR gate to solve this, right? This would be a solution. There's actually a challenge and achievement that demands us to only go by 4 NAND gates. Question is, how do we connect them? Okay, this is not AND, right? This eliminates this case, right? So, if we eliminate this case, we have to eliminate this case. A guess, to be honest. This is the trick. So why does it do the trick? Okay, so when we're here at this stage, it eliminates this case, right? The next stage do? The next stage checks if one of these are true, and this is not true. Maybe are true, or they're false. If this is true, right? If this is true, then it's either one of these 3 cases, right? So if it is this case, let's check this case. This is true, because this is always true. In this case, these 2 are true as well. Both true. Makes sense. Makes sense to me. I hope it makes sense to you as well. So the bigger OR gates, the bigger AND gate. These levels are quite easy. Create an OR gate with 3 inputs. Since we already created our OR gate, we can just chain our OR gates together. And have an OR gate. Like an OR gate is true. I feel like I should say this. An OR gate is true whenever one or more of the inputs are true. Maybe I should have named my camera. Here we are. I'll do lighting as well. So now we have the bigger AND gate. This is true when all the 3 lights are on, which is also just AND gates chained together. Let's make it beautiful. Completed. Here we are. With the X NOR gates, create the inverse XOR gate known as the X NOR, exclusive NOR. This is a negated or XOR gate. It's pretty The XOR gate is an exclusive one. It's only true when one of these 2 cases are true. If we negate it, create the inverse of that, which is if both are true and both are false. Here we are, the X NOR gate. Onwards. Odd number of signals. Double trouble, binary eraser. Circular dependency. What are we going to? We could take this line. Circular dependency. Odd number of signals. Double trouble. Binary eraser. We can do this. This is. Decimal numbers. Toggle the bits in the level panel so they add up to the decimal number in question. You must beat level 3 to pass. Click here to turn on timeless accessibility mode. No, we don't need that one. We have to convert some numbers into their binary counterparts, which is, if I were to explain it, the first bit. Like if we want to express numbers in binary, right? We would use the binary system, where the first bit represents the number 1, the second bit the number 2, which is 2 to the power of 1. Okay, while 4 is 2 to the power of 2, and this level is basically designed to demonstrate the fact that you can basically, oh, this is 31, 32 would be the next number. You're basically able to, I don't know which level we need to reach to pass this. Like you can basically express every number imaginable within this system. Oops. No, I failed. Good job, you've reached level 4. Okay. Hopefully you noticed there's exactly one way to write each number in binary. The value of each digit is always double of the previous digit, yeah. Oh, I completed the level. There's enough. Great. Double trouble. Because we are so technologically advanced, we have machines fold our socks. Unfortunately, the circuit that detects sock pairs broke on the machine. This level has 4 inputs. Output green when 2 or more of them are green. Don't overthink this level. 2 or more. Don't overthink. It's probably just a big chain around guys. This would work. is true. This. That is true. No, this would be the last one. But if this one is true. If these are true. This is 6 possibilities. This is basically just depicting every single possible pair that could come across, that we could come across. And if one of these pairs is true, output true. Does that make sense? Hope so. Not to put odd number of signals, circular dependency. Let's go with this one first. Using a maximum of 3 components, output green only when an odd number of inputs are. Okay. This level has a hint. You can use it before it's stuck. Nice. Okay, only an odd number of signals is true. This is gonna be a chain of these OR gates. By the way, I so recommend you to play this game without my guidance. This is gonna teach you so much. I remember playing this level for the first time, breaking my mind about how this is done. But yeah, it really makes sense. Wait a second, let me figure out why that is. Yeah, if either one of these is true, right? If it's an exclusive OR, then we have an odd number of signals. So if we have an odd number of signals and we feed another signal into it, right? Like this gives us odd or not. True or odd. If we have odd and we add 1, we have even, right? And if we have even and we add 1, we would have odd again. Does it make sense? I hope so. To me it does. Right, for this. Anyway, we're going to continue this series. I'm going to show you the basics of how assembler works. At the end of the day, this is a game, right? It gives you a blueprint of how you would how we go from electronics to digital logic, and from digital logic to an assembler. And once we've created an assembler, we can make our jump to things like actual real-world assemblers like ARM, RISC-V, and there are actually people who've built some functioning, and I started as well doing this on another account. They've actually built functioning RISC-V CPUs, which I find to be so impressive. And I find to be so cool. And in a sense, I love this stuff. I really do. Let's see how far this rabbit hole will lead us. Maybe if I replay this game, I'll actually finish the RISC-V CPU with you, and we'll see where this leads. I remember having trouble because there are... I'm gonna see this later. But I'm gonna tell it to you anyways. There is like, I don't know, once we've created an architecture and we create an assembler, right? Maybe you know a little bit about this stuff. You would have these sets of instructions, right? And that you basically define yourself. And I've actually taken a look at ARM and taken a look at RISC-V as well. But it is not that easy to and sometimes I feel like maybe this is because RISC-V is just so free that a lot of instructions aren't hard defined, right? Maybe, I don't know, if you know something about this, you might be able to help me with that. Because, I don't know, instruction sets are basically 32-bit if I remember, or 64. I'm not quite sure. And there are different types of instructions. And it's not, I don't know, from the manual that I've had, I wasn't able to clearly conclude which instructions were meant for what, and yeah. And maybe this because RISC-V is so free. I hope my question makes sense. And yeah, if you have no idea what this shit means, or if you have no idea what this stuff means, maybe we'll get to a point where we'll get a clue. And I hope so. And if you play this game up to the Water World Challenge, I think you will be able to understand what I mean. Probably already in the functions section. This was so much fun. Yes. But for now, this is gonna be the video. This is gonna be the video. This is gonna be the video.